Good morning, everybody. Thank you, Ernesto. Thank you, Corey. Okay, so last time I started talking about integration theory in complex functions with complex variables. So the main thing, the main point is in complex analysis, we always integrate over a curve, okay? We integrate over a curve. Now, here is a brief just review of what I did on Tuesday. To begin with, you have a function, complex, and you have a curve. Of course, the equation of the curve either is given or you are supposed to find that curve. And whenever we talk about curve, we need its parameterization, of course. So the function here is has real part plus I imaginary part. As soon as you have the curve, its parameterization, the way we integrate is just replacing the parameterization in here. You will have f of z of t, z prime of t dt. And in the process, the first fact that I talked about is ML inequality. ML inequality, by the way, when you are integrating over this curve, M is upper bound of modulus of f of z on that curve, and L is the length of this curve C, okay? I gave you an example last time, so I don't want to spend a lot of time on it. Then here is when we use parameterization, and you replace f by u plus iv, dz by dx plus I dy, and this is what you get. And the evaluation of these two integrals goes back to calculus 3, okay? Among the important formula that we discovered was the integral of dz over z to the n. When n here is 1, the integral of dz over z, then you integrate over this unit circle or any circle centered at 0. Radius doesn't matter. You will get 2 pi I when n is 1. Otherwise, you get 0. So we computed this and we went through it very carefully to make sure that you realize this one, okay? Then the question was, what if the center is not 0? Center is at, let's say, a point, a complex plane. Then you need to integrate over a circle centered at the same thing. Radius, again, doesn't matter, right? When n is 1, you get 2 pi I. When n is different from 1, you get 0, okay? Well, today, I want to talk about Cauchy's theorem, and it is a fascinating theorem, and it applies to a region that is called simply connected. So a region of a XY plane is called simply connected if there is no hole in it, all right? It's open and connected. Connected means any 2 points can be joined by a number of, let's say, line segments here. This one is connected. And actually, it is simply connected because there is no hole in this one, all right? This line segment indicates that, look, this point and this point can be connected by this. So this is a simply connected domain. This is a simply connected domain. This is not, because there's a hole in it. All right, there's a hole in it. Cauchy's theorem applies to simply connected theorem and simply connected domains. And in the proof of Cauchy's theorem, we use the Green's theorem, right? We use Green's theorem of K+3. But the proof is not that important, but the statement is fascinating. Here is just as a reminder what Green's theorem was, because in the proof is being used. Green's theorem is about a line integral of a vector field. Okay, this is K+3. P and Q are functions of two variables, X and Y. There's no complex stuff here. No, I'm just taking you to K+3. So Green's theorem says if you are integrating P dx Q dy, by the way, this is another way of writing this is F dot dr. R is the, in this case, the boundary, all right? Think about R being this boundary. Green's theorem says you can convert this to a double integration, but when you take double integration, you have to do the double integration over a region of XY plane. And that region is the area enclosed by this boundary. Okay, this is the boundary. So double integration over this D. Of course, it will be partial of Q with respect to X minus partial of P with respect to Y. And then this is element of area, which is either dx dy or dy dx. This is Green's theorem, all right? Now, the nice thing about Green's theorem is if the vector field here is conservative, and the vector field being conservative means partial of Q with respect to X is the same as partial of P with respect to Y, this will be 0. And as a result, the line integral of this vector field over any closed curve will be 0, okay? So, but you saw those things in K+3. I'm not going to spend more time on it. Just a reminder that what this Green's theorem is. So here comes the Cauchy's theorem Cauchy's theorem is for complex function. It assumes that derivative of that complex function exists and is continuous in a simply connected domain. So there is no hole in a simply connected domain. And if C is a closed curve in that simply connected domain, then the integral is zero. Okay? The integral is zero. Very, very beautiful theorem. As soon as you are integrating a function which is analytic, and in Green's theorem, well, there's this condition of f prime be continuous because, as I said, in the proof we use Green's theorem, and in Green's theorem we need the continuity. All right. The proof, of course, is right here after writing in f as u plus iv, dz as dx plus I dy, and multiplying out. Since the function has derivative is analytic, we are going to use this Green's theorem. And Green's theorem converts this and this to double integration. And now you use the Cauchy-Riemann equations. And Cauchy-Riemann equation tells us that these two, this will be zero, this will be zero. So the result is zero, okay? This is Cauchy-Riemann equations. So, okay. So the message is pretty clear. As soon as you are integrating a nice function over a closed curve, the result is zero. Okay, the result is zero. That is Cauchy's theorem, integral theorem. Now let's see if I have sort of some, yeah. So here is the summary, the statement of Cauchy's theorem. Now it seems that it's a little blur. Let me change the camera. Hopefully by changing the camera, we'll get sharper, the sharper picture. Okay. So here is Cauchy's theorem. If prime of z is continuous, do we really need continuity? Later we will find out that no, we really don't need this continuity, all right? But in a simply connected domain D, here is the simply connected domain, doesn't have any hole in it. Then if you integrate over this closed curve, the result is zero. The result is zero, okay? And again, I emphasize that if we use Green's theorem in the proof, we definitely need the derivative be continuous. But later, another mathematician found out that, yeah, we really do not need that continuity. But here is an example, right? Here's the example that, look, we are integrating this function over unit circle. It could be any closed curve. But the fact is, the function is a beautiful function. It's analytic, its derivative is continuous, everything is there. So the integral is 0. Here's another example. I am integrating this function, 1 over z squared minus 4, over the unit circle. Oh, here is the unit circle, right? Here is 1. But the roots of the denominator, which makes it really bad points, are plus minus 2. They are outside this unit circle. I am integrating over this curve, and the function is perfectly beautiful function here. All right, all the conditions are there. As a result, the integral is 0. Okay? Two examples showing you how things works. As I said, the continuity is not really needed. We only need to know that derivative exists. As soon as derivative exists in a simply connected domain, if you integrate over a closed curve in that domain, the result is 0. Okay, the result is 0. This is the improved version of Cauchy. Cauchy required the continuity of f prime, but later another mathematician, Goursat, realized that he could prove the theorem without using Green's theorem. And in his proof, the continuity of f prime was not needed. So from this point on, we will use this version, which is the improved version, as long as you know derivative exists in a simply connected domain, no hole, then integral over any closed curve will be 0. Right? Integral over any closed curve will be 0. So, any comment, any question? This is a extremely important theorem and is the foundation for integration theory in complex analysis. So you need to know that f prime exists. Another way of saying it, you need to know that f of z is analytic in a simply connected domain. Analytic means a derivative existing at every point. Whenever you have a closed curve in that domain, the integral over that closed curve is 0, right? Any comment, any question? I don't see any question. I will continue. So the question, of course, will be, what if we have a hole in that domain. Is this Cauchy theorem still valid? Well, that's pretty interesting. Here is a domain with a hole. All right. Here's a domain. This is a hole in it. So I have this outer boundary and this inner boundary, all right? Well, if there is a hole, I can cut. I can make a cut here and a cut here. So I will divide this into two parts. Now here in the part one, there is no hole. So the integral over the boundary is 0. And always when we integrate, we go counterclockwise, all right? Counterclockwise. So going counterclockwise means, right, we go here, this one, and come back. All right, and right here. This counterclockwise. Do the same thing also counterclockwise, all right? Counterclockwise means going in this direction now. Coming to this point, going this way, to this point coming this way, and so forth. So if there is a hole, we can cut. We can have two cuts and then apply this Cauchy-Goursat theorem on part one and part two. If you use it in part one, this is what you get. You integrate from G to C, right, from here to here. Then you go C, B, A, then A, E, and then this one. Okay. Since there is no hole based on Cauchy's theorem, the result is 0. Do the same thing for part 2. For part 2, you start from doing counterclockwise, C to G, then this one, G, H, E, then this one, and so forth, all right? But after integration, you add these two. The integral over this, and it's changing the orientation. When you change orientation, it should be negative of that. So this and this cancels, this one and this cancels, and the result will be, look, I'm integrating over this up to here and this. So the outer boundary, the combination of that and this will give me the integral over outer boundary. But the combination of this one and this one gives me the integral over inner boundary, but clockwise. Oh, look, this is clockwise, that is counterclockwise. So I can change the direction. So outer boundary plus inner boundary clockwise. So I can change to counterclockwise. There will be a negative sign here. Take that to the other side. You will get this. So if there is a hole in there, the integral over outer boundary will be the same as integral over inner boundary. Okay? This is extremely important fact. I just gave it to you. So this plays an extremely important role in what we do. So let me give you examples. One example here. Here's one example. These examples, I hope, will clarify what we are doing. Okay. Well, this is in fact, yeah, a combination of something that's yeah. Let's have some examples here. And the consequences, maybe okay. As I said, we saw this one earlier. This function is beautiful function. Every has derivative, all right? So as soon as you integrate over a closed curve, the answer is 0. Here's another example. The bad point here, the bad point usually are zeros of denominator, is 1. And here is 1. I am integrating over this circle centered at -1, radius 1. So this is the curve, the closed curve that I'm integrating. The bad point is outside, but the function is a beautiful function in this area, right? So the integral over this, because the function is analytic in this, is 0. What I proved now regarding that hole, if you have a bad point inside and you are integrating over this, you can isolate that bad point. And think about this as a domain that has a hole in it, okay? Has a hole in it. So the integral over outer boundary will be the same as integral over inner boundary. This is what we need. So if you have a bad point inside, the integral over outer boundary will be the same as integral over inner boundary. Okay, how do we use this? Here is how. Here is how. I want to integrate over this curve. Right, it is a closed curve. What is the function that I'm integrating? This is the function. The bad point is inside. Okay, the bad point is inside. We isolate this bad point and then use the Cauchy's integral theorem for the case that you have a hole. So the integral over this outer boundary is the same as integral over this inner boundary. Well, so the integral over that outer boundary, I will make this one a circle of radius 1. So it will be, the center is I, z minus I equal 1 modulus, all right? And earlier, we noticed that this is 2 pi I. This is 2 pi I, okay? Any comment, any question about this 3 examples or 2 examples? Okay, I don't see any question. So there are very nice consequences. By the way, I talked about one hole, but there could be several holes. Okay, there could be several holes. In fact, there could be n different holes. So what we do, we cut, we make this cut here like this, right? And apply these cuts. We divide this into 2 parts, top part and lower part. And we apply the Cauchy's theorem on those. Yeah, we will get this. The integral over the outer boundary is the same as sum of the integral over the inner boundaries, these holes, okay? This is important because you might integrate a function that has more than one singularity, more than one bad point. You isolate those bad points, all right? An integral over the outer boundary will be equal to integral over the inner boundaries that when we isolate those. Now, here is an example. Oh, look at this. This function has 2 singularities or bad point, zeros of denominator. Yeah, we don't like zeros of denominator. The term that we use, the official term, we call them singularities. But for the time being, let's just say bad points. So if you go through a denominator and do partial fraction, so this is what you get. There are 2 bad points. One is z equal 1. The other one, z equal -3. So here is z equal 1, z equal -3. And we are integrating over a circle of radius 3 centered at I. Here is I. And radius is 3. So this circle, the curve that we are integrating over, is missing this bad point. Okay. We are integrating over this curve, this circle of radius 3, centered at I, it misses this that point, but no, this one is inside. So I use the fact that the function is a nice function here. This is outside, I don't really care. The integral over outer boundary is the same as integral over inner boundary. Okay? So this is what I get. Oh, here's after doing partial fraction. So the integral, I only need to integrate over the inner boundary. But this one, if I integrate over this, the function is a beautiful function. The back point is way outside. So integral is 0. And this one, based on what we learned earlier last session, is you can bring 3 out, then that one is 2 pi I. So the answer is 6 pi I, okay? 6 pi I. Any question, any comment? No question. Okay, good. This is so because of its significance, I'm going to repeat this many, many times so that you get the exact point, right? So the Cauchy-Grossac theorem says if there is a hole, and the function is analytic in here, derivative exists, analytic. Oh, okay. Del Dodson is asking about. All right, here. Let me show you the. So there's no question that this is 3 times 2 pi I. But this one, okay, let's see. Okay, here. This one, we are integrating a function. The function is 2, doesn't matter, divided by z plus 3 over this curve, this closed curve. The closed curve is this one. Okay? The center is 1. If I integrate over this curve, the function, this function, doesn't have a bad point here. It's analytic here. So Cauchy's theorem said when you're integrating a function that is analytic on a closed curve, right? And here, then it is 0. Here we are applying Cauchy's theorem. So here, this is not going to be 2 pi I. If, oh, by the way, yeah, let me make sure. If I was integrating over the circle centered at this point, over this circle, let's say right here. If I integrate this over this circle, where the center is right there, then it would be 2 pi I times another 2, 4 pi I, right? But right now I am integrating over this, which is this function is analytic. And for this one, I'm using Cauchy's theorem, 0. Any sense? You're welcome. Okay. So going back to the same idea. So remember, as when you have a bad point, we usually isolate that. And that is when we get a hole. The integral over outer boundary will be the same as integral over inner boundary, okay? Now, here's another example. These examples should hopefully clear the messages or theorems, and hopefully will give you a better understanding of Cauchy's theorem. It says, integrate this, dz over z. What is C? It says C is the boundary of rectangle with vertices this. So here is the rectangle with vertices being given. Okay, here is 3, 2. Here's negative 3, 2. Here is negative 3, negative 2. And here is 3, negative 2. So vertices are given. This is the rectangle. We remember, in complex, always we integrate over a curve. So, but the bad point here is 0, which is here. So we use this unit circle. Then you get a domain with a hole in it. So the integral over this, call it C, is the same as integral over this. Here is how we use this whole business. So the integral over C is the same as integral over this unit circle, but we know the integral over that unit circle dz over z is 2 pi I. Done. Right? Any comment, any question about this example? No comment. All right. Well, I'm going to give you another example. So I want to integrate this over circle of radius 9, centered at 0. Okay. But there are 2 bad points. There are 2 bad points here. Okay. One bad point is 2, the other one is 6, because denominator z squared minus 8z plus 12 can be factored. Z minus 2 times z minus 6. So there are two bad points, z equals 2, z equals 6. And both of them are within this circle that we want to do integration. So we are going to isolate both of them. So the integral over the whole thing, the outer circle, will be equal to integral over this one plus integral over this one. Okay? So this is f of z after doing the partial fraction. Well, let's do one at a time. So you are going to integrate over the unit circle centered at 2 and the unit circle centered at 6. But when you are integrating over the circle centered at 2, unit circle, this will be outside. So this goes away. So the integral of that is 0. And when you're integrating over this circle, this part, which is analytic, the integral of the first will be 0. So you'll get only the second part. And now use the fact that, see, the center are the same. Now this is going to be 2 pi I. Here, you're integrating over the center, centered at 6, z minus 6. That is 2 pi I multiplied by 4. So the answer is negative 6 pi I. Okay? Another good, very good example. Very good example. Okay. Well, I gave you enough examples for this Cauchy's theorem. But just summarizing, again, as I said, it doesn't matter how many times I repeat this, because that is the foundation for integration theory and complex analysis. This is how, if we have parameterization, this is how we use and integrate. But if you have a closed curve, if you are integrating over a closed curve, and the function is analytic, the result is 0. Okay? If the function is analytic, but there is a hole in here, analytic in this washer, then the integral over outer boundary is the same as integral over inner boundary. How about if we have more holes? If you have more holes, this is what happens. The integral over outer boundary is the same as a sum of the integrals over these. Okay, so that is the any comment, any question about this sort of brief explanation? Okay, well, there are a number of consequences for this Cauchy's theorem. okay, a number of consequences. Here is one of them. If the function is analytic and in a simply connected domain, analytic here, and you are not integrating from on a closed curve, you want only integrate over from z naught to this point. Well, remember, in complex, we always integrate over a curve. So we need a curve going from here to here. When a function is analytic, the question is, does it matter which curve we choose? Can I choose just a straight line? Or this, or this? The answer is, it doesn't matter. So the answer to the integral is independent of these curves. Why? Oh, here is why. Suppose you choose two curves, C1 and C2. Well, combination of C1 and C2 will give us a closed curve, right? And we know that the integral over a closed curve is 0. But when you go from C0 to here in this direction, and then come back, the integral will be 0. But we can change the direction here, and the effect will be a negative sign. That means going from 0 to z on C1 and going from z0 to z on C2 will be the same. Okay? So this is one of beautiful consequences of Cauchy's theorem. So if you integrate from a point to another point, and the function is a nice function, the answer is independent of the curve you are choosing. You can choose the easiest curve you can find. The other fact, the other consequence of Cauchy's theorem is that the antiderivative, if the function is analytic, all right, the antiderivative exists. Well, proving the antiderivative exists, yeah, if this is for integration, but just using CAD. Proving that antiderivative exists is we use the constructive argument. So if f of z is analytic, if you define the function from z naught to z, f of z dz, since this function is analytic, the value doesn't depend on the particular curve you choose. But interesting enough, this is a nice function. Oh, this is a nice function defined in terms of integration, fine. And we can easily prove that its derivative is this one. So if the function is analytic, its derivative exists. That's a very interesting, I would say, second important consequences of the Cauchy's theorem. Okay, second consequences of Cauchy's theorem. But now I'm going to give you this is a proof of the theorem, but I'm not going to spend time in proving that antiderivative exists, okay? Instead, I will go to, yeah. So if you're integrating and the function has an antiderivative, the evaluation is pretty simple, okay? Here, I want to integrate 2z dz over this curve C. What is the curve C? The curve starts from here, goes all the way along the circle up to here. So here's the straight line. So pretty complicated curve. But since we have antiderivative here, which is z squared, the integral is going to be just z squared evaluated at the endpoints. We want to go from here to there. So this is from 1 minus I to 1. But this is the answer. Okay. Here is another example of such phenomena. Okay, suppose we want to integrate this and the curve is y equal x squared, this one. And we want to integrate from this point along this curve going to this point. So usually, in this case, the function that we are integrating has antiderivative. So, but if it doesn't have antiderivative, you need to parameterize this and do work with the parameterization. But in this case, it has antiderivative. We find antiderivative, evaluate at this point minus evaluate at this point, right? So here is from this point to that point, its antiderivative is right here. Evaluate at this point minus evaluate at this point. That gives you the answer. All right. Okay. Well, now this pretty much covers 14.2, and I gave you a number of examples to make sure that you feel comfortable with it, all right? And the next thing is what we call Cauchy integral formula, which is the only formula you need in section 14.3, I believe that is, yes. So this is Cauchy's theorem. I'm repeating it, which is perfectly fine. If there is no bad point, the integral over the closed curve is 0. Okay? But what if there is a bad point and this is the bad point right here. And the curve that you are integrating, the bad point is inside. Okay, the bad point is inside. Well, it's very simple. There is a very beautiful proof for it, but I'm not going to go through proof. So if f of z is nice, but here is a bad point in the denominator. If you integrate over this closed curve, the answer is 2 pi I, the function evaluated at this bad point. Okay? The function evaluated at that bad point. That is called Cauchy's integral formula. Cauchy's integral formula, right? All right. So let's see if okay. Yeah. So I will go through this Cauchy's integral formula in more detail next time. But I will stop at this point just today. Today, I reviewed the integration theory in complex. All right. So I reviewed 14.1 and 14.2. I completed the section 14.2. And because of its significance of Cauchy theorem and its consequences, I spend a lot of time to make sure that you guys understand that major theorem. Well, I gave you quite a bit of examples, so hopefully those examples will help you to completely understand the concepts. And please go ahead and read 14.1, 14.2 examples. And if you have access to another textbook, sure, start reading these integration concept and then do the homework problems. Any comment, any question? Well, if you don't have any question, then I don't see any question. So have a good day, everybody.